Welcome back, everybody. In this episode, what I want to talk about is loss, accuracy, and optimization. And first, let's talk about loss. And I don't mean what's happening with GameStop Corporation and all the loss that the world is feeling about that particular situation. What I actually mean is loss in terms of our neural network, and not just in a neural network, but loss, calculating the loss overall. And so I've showed this graphic before, but I want you to consider, forget what it's called or where it falls into, but let's just really focus in on the concept of what's going on here. And, we've got this line and we've got some errors here. Okay, so based on where the points sit on either side of the line, we can identify that we have two errors. But as we're able to move the line, we can reduce the actual errors, right? And which is the ultimate goal. And again, we can get down to 0 errors. And I want you to think about this again in a different sort of a visual context. Okay, because our ultimate goal is to minimize our error function. That's what we really want to do here. We want to make really, really accurate, great sound predictions. Okay. And so let's go back to this. And when we look at our errors, we see that we have 2 errors, right? And they're large penalties. And the reason this graphic is so good, because it puts it into scale, some sort of a contextual scale of really what's going on in terms of loss. And we calculate all of the points and we assign a large penalty for the 2 errors that we have. And we have a larger sum, a larger number that results. But when we eliminate the errors, we get them down to 0. Graphically, we can see that our penalties are smaller for a more correct score or a more correct sum. So this is really what we want to do in terms of our overall prediction, and is sort of a measurement of our loss. And one way people like to sort of look at this is their loss function. And the loss function quantifies how unhappy you would be if if you use W to make a prediction on X, when the correct output was actually Y. Okay. That's a bit of a tongue twister, but we're going to actually get into the code. Don't worry. That's going to happen soon enough. But this is really, the loss function. This is root of it. It is the number we want to minimize as much as possible. So ideally, we can get to 0. That's really what we want to do. And if we go back in time and we look at this example, this training data, and we've got these inputs, and we're going to our learner sort of function. Right? And we're trying for that prediction. That's what we want. In a more simplified form here, if we just look at the learner, we see how the learner feeds into the other part of this code here. But really the learner is going to break down into optimization. Okay. And this really means, what do we compute and how do we do this? So I don't want to do too much in here in the PowerPoint piece. I think today I really want to spend time just doing more code, less on the slides. So let's get into the code. Before I start with the code, just to be fair and remind everybody, as always, this particular section of the video series, I am taking the information directly from this book, Neural Networks from Scratch. And all the animations are coming from this particular book and the website. So if you're following along, this is where I'm getting it all. Okay. So I'm also following along with the actual numbers in case you do decide to make that purchase. You can kind of follow along and do both. Anyway, to full disclaimer, I have no affiliation with the authors of the book. I just think it's an outstanding resource for people to learn about machine learning in general, but also, specifically to neural networks. But there's so much in a neural network that has to do with machine learning that I just think it's a good way to scaffold your learning and understanding of machine learning using this. And so I've said kind of before in the past, I think that if you've never seen an automobile before, and I said to you, today we're going to talk about the carburetor, but you've never seen a car, how can you contextually understand what I'm trying to get at? And so that's why I've chosen to go to this actual book and to start with the neural networks, because there's just so much about this. It is the proverbial car. Okay, so let's go over to where we left off here in our neural network. And I think one thing I am going to do is start adding in some notes. Okay, and I want to do a really quick review. You can skip through this if you've been following along in the past, but I want to do just a really quick review on where we are with this before we get into calculating loss in some other things that I want to do today. So up here, what I've taken from the actual book, the authors of the book, is they actually created this randomized data. And when you look at on a scatter plot, this is what the result is. So this is our data set. And down here is where we started to actually build out the classes and some functions within the classes. Okay, so this first one here, this layer dense, the comment that I want to put in there is that it is right here. And of course, these comments are coming from the book as well. And I want to say that initialize weights and bias. Okay, so I'm going to put that comment in there. And as we go forward, what's happening is now we're getting into the forward pass. Okay, and this is going to calculate the values from inputs, weights, and bias. Okay, so that's really what this particular thing here does. And if I put the comment, it is forward pass. Okay, and let me do a comma. Calculate outputs from inputs, weights, and bias. Don't really need a comment above the activation Relu or Relu, depending on how you want to say it. And you can see that we've got another forward pass in here, right here. And this is just, again, a forward pass, which is the same thing down here with our activation softmax, right? Same thing. And I'm going to take this comment here and just copy it and make a slight modification here, because it doesn't take the full weights and bias, right? It's just the inputs right here. Okay. And what is it that we know about this particular output? Okay, we know that this one is, this produces an unnormalized output. So we've got negative values in here. And if I go down into my activation softmax, I want to put a comment right here that says get unnormalized probabilities. Okay, unnormalized probabilities. That's what I'm getting at this point. Okay, and then the next line here, what I want to write is normalized, or normalize, not ED, normalize them for each sample. Okay, so now each sample is normalized, meaning we've now accounted for the negative value. Okay, because as you know from the last time watching, we can have negative meaning, but we're trying to normalize it so that and we can't normalize it and set it to 0, because if we set it to 0, the absolute value of it will be lost. But we're still trying to maintain the meaning of the number or the sample, but just not in a way that it is set to a 0. Okay, so for example, if I said, -5, the absolute value is 5, but the minus, we don't want to have a minus number. So we're still trying to hold on to the meaning of 5, just don't want the negative value. And so that's what we're trying to do there. And of course, this whole step here is to set our probability. Okay, and that's what we want, is to get a probability of this happening. All right, and then the probabilities we're setting to our output. Okay, and then finally within this piece, what we're doing is we're actually creating a data set, and we're getting the data set from basically here. So this whole entire block of code is meant to create this randomized data. But down here, we're saying, okay, now we want to get it and actually use it. Okay. And within this data set, we're saying, give us 100 samples. So you'll see here, there's 100 red, there's 100 blue, 100 green. But I also want 3 classes. Okay. So I want, I've got red, blue, and green. That's 3 classes. Okay. So that's why we're doing it in this way. So if I go inside this next cell here, I'm going to go down and I'm going to type in a comment. And what I'm going to say is create dense layer with 2 inputs. And, 2 input features. 3 output values. Okay, so that's what I'm saying there. I want a dense layer with 2 input features, 2 things coming in, and 3 output values. And so next what I want to do is look at this next one, and I want to say create Relu activation for the dense layer from just above. Next, I want to basically create a second dense layer with 3 input features, and as we take the outputs from the previous layer, and then 3 output values. Okay, so we're getting 3 and 3. Okay. Now, you might be asking yourself, why is this now 3 and 3? And we need to match up this second parameter, this output value, these 3 output values in the next layer to match. So these now become our 3 inputs. Okay. The next thing that I want to do is create the softmax activation for use in the dense layer. Okay. And we call this one activation 2, right? Because we have activation 1 and now we have activation 2. And so after that, right away, what we want to have is make a forward pass of our training data. Remember here, so we're talking about this X in the cell above in line 28. So we want to make a forward pass of our training data through this layer. Okay, so I'm passing X through here. So immediately after that, this activation 1, okay, dot forward dense layer. So what are we doing here? What we're actually doing, let me give it a little bit of space. Okay, is we make a forward pass to the activation function from the output of the first layer, okay, from this output here. All right, so that's the thing that we just did next. So for this next one, this one's a longer message. Make a forward pass through the second dense layer, takes outputs from the activation function of first layer inputs. And then finally, what we're doing here is we're just printing out activation 2, what the final result is, but we're only looking at the first 5 outputs. And what's really interesting to note is that each of these predictions actually add up to almost 1. They're as close as 1 as you could probably get, okay? So if you added up each row, they would all come out to roughly 1. So a really interesting way to look at this is to say that the output of a neural network is actually confidence, and more confidence in the, answer is better. And so we're striving to get correct confidence and decrease our actual lack of confidence, if you will. And so what I want to do is just really quickly go through the book, and it talks about categorical cross entropy or entropy loss. And because we're classifying and not actually performing regression, we need a different kind of a loss function. So if you look at this, our model has a softmax activation function for the output layer, which means it's outputting a probability distribution. Okay, so this is all a probability distribution. I'm going to spend a little bit of time just explaining this categorical cross entropy loss. And there's a few things to know about this. And it compares the ground truth probabilities or targets and some predictions. Okay, and you may have heard the term ground truth if ever you were dealing with maybe some computer vision as well. Okay, but it's, what is the actual real truth that's currently happening? That's what we're talking about. So we're comparing the ground truth probabilities or targets and then some predictions. And it's one of the most commonly used loss functions with softmax activation for an output layer. Okay. And then finally, you may be, depending on what your level is or experience level with this, you might be saying, well, why not log loss? And I'm going to explain that right now. So log loss error function is what's applied to the output of a binary logistic regression model. So there's only two classes in the distribution, and each of them is applying a single output neuron, which is targeted between 0 and 1. Okay, but in our case, we have a classification model that returns a probability distribution over all of the outputs. Okay, so cross entropy compares two probability distributions. So let's go over to the code and see what this means in a different way. So I've started this other notebook here, and let's say we've got our softmax output, and we got 0.7, 0.1, and 0.2. Okay. So when we talked about this before, we said that, we have our probability distribution. So if you look at this, we're saying, this is our probability distributions. And our probability distribution, which one do we intend to compare this? Because we have three class confidences, okay, in this particular example. And let's assume that the desired prediction is at index 0 here, this first one, 0.7. Okay, if that's the intended prediction, then the desired probability distribution would look something like this. Okay, it would literally look like this. Okay, so our confidence in the very first one would be a 1, right? Our absolute 100% guarantee is what we're trying to get to as close to 1 as possible and furthest away from 0. So if this is the one that we want at index 0, this is considered, something is referred to as one hot. Okay, meaning one of these values is on or hot and the other are cold. So it's saying one of them is hot, so that's why it's called one hot. Okay, and the one that's closest to the value of 1 is the hottest one. Okay, I shouldn't say, it's closest to 1, it should be 1. And the target's probability log loss is multiplied by 1, making the cross entropy calculation relatively simple. And this is a special case of the cross entropy calculation called categorical cross entropy. So, this may be a little bit hard to understand, but, as we get into the code piece, it should be a little bit more intuitive about what I'm trying to say. But let's do this. Let's just look at an example. Okay, so I'm going to say target underscore output. Okay, and above this, I need to do math. So import math. Give myself a little bit more space. And I think that those values are just fine. And we're going to do this loss. Okay, and this loss is just follow along in what I do here. Oh, not 90. If you see me type a 90, it's because I missed the bracket. So I'm going to do this math dot log. Okay, and in here it'll be softmax. Softmax output at 0. And then multiply by target. That's not right, but it's close enough. Target output. Okay, multiply that target output and at index 0. Okay, and what I want to do is add this, and then I'm going to just move this down to the next line. I'm just going to repeat this a few times. Actually, before I repeat that, I need to move this bracket over to here. And now I can repeat this a few times. Change these to 1, 1, 2, and 2. Get rid of this. And I should be good. I'm hoping that's correct. And then print loss. Okay. Okay, and we get this number here, this 0.35667494. Okay. So when we look at this calculation, what we're actually doing is we're focusing in on not these second two numbers, because, you know, in reality, any number, doesn't matter what it is, which is these two, multiplied by 0 is still going to be 0. So the assumption here is that we don't really have to look at these two numbers here, right? We really don't. But in this particular case, in the calculation, we've added it. All right. And so ultimately 0.7 times 1 is just going to be 0.7, right? So really another way of just saying this, and I will get rid of these two lines. I'll get rid of all of this. In fact, I don't need any of that. Do I need to keep the brackets? Don't really need to keep even the brackets here. So if I do this and then I say, you know, what is the actual value? I run that. It's actually the same exact number, right? So the log of the softmax output at 0 index or 0.7 is 0.3567494. Okay. So ultimately all I need is the softmax output of that. And then I'm using my math.log function right here to make that loss calculation. So, you know, you look at this example here, we've got 0.33, 0.33, 0.33. But let's suppose we had an example where it was, you know, look at this one here, 0.7, 0.1, 0.2. All of those add up to 1, right? So I want to say that it stands to reason that the larger, or let's say the lower the confidence, the larger the loss is going to be. Okay, so when we look at this and we're talking about confidence, these ones are all almost equal. Okay, and in this case, we look at it and say we have a low confidence level here for 0.1. Well, that implies that you're going to get a larger loss. So I'm just curious, what do we do if we change this to 1 and we change this to 7? Okay, and then I run that. You can see that now I'm getting an output that is a much larger loss. Okay, and let's try and we'll undo that. And let's say this one here. Make this 7, we'll make this one 2. Okay, if I run that, and you can see how it corresponds to that, and that just intuitively makes sense. So let's look at this in one more way. So, you know, the closer to 1 that I have as my number, okay, we look at the value of the loss. So if I run this, you can see that I get a loss of 0. Okay, so this is the, this is the most desirable outcome. And what it is saying is that if the confidence level is 1 right here, then it means that we're 100% sure about our prediction. Okay, so the loss value for this sample equals 0. We have 0 loss. Okay, that's what we're trying to get at here. Let me try a couple more of these. Now let's see what these say. All right, look at these numbers here, right? Big drastic change here. So what we've done is we've actually applied the logarithm to the softmax output. And, you know, it doesn't really matter why just yet, but we'll get to that. But I want to talk about this logarithm just for, if anything else, just a review, right? So we've got this idea of a to the power x equals b, and you can represent it another way. So 10 to the power of x is equal to 100, but it can be represented in a different way here. So we use this logarithm with the subscript of 10 to equal 100. So you can see the one just above it in the one with the log is really the same representation written in a different way. And then when we look at this Euler's number, this 2.71828, and this applies for when the base is actually 10. We've got this example here where we say that Euler's number to the x equals b. Okay, and so that whole thing we're talking about is the natural logarithm. Okay, so when we refer to logarithm just for short, this is really what we're talking about, this idea here. And finally, if we say, you know, x or Euler's number raised to the power x equals 5.2, again, it's really just log 5.2. That's what we're trying to say here. Let me go back in here and clean all of this up. Okay. And I'm going to run this just to see if it'll clean or if I have to delete it. It doesn't matter. But one thing I will do now is I'm going to do import numpy as np. Okay, so we're going to use numpy. And then if we say that b is equal to 5.2, now what I can do is I'll go down to here. Yeah, why not? I'll go down to here. I just didn't want to go into the next cell. But if I say print np.log, and inside the log I say b. Okay, let's check and see what we're getting here. Let's run this. And you're seeing that I'm getting this number, this 1.64865.862. Okay, so that's what we're getting as a result of that. And let's just do one little thing. Let's try and see if we can get back to B. And the way we're going to do this is like we've done in the past already with math.e and then 2 multiplications. And I guess we can take this number here if it'll let me copy it right here. There. And so let's run this and see what happens. You see that I get all the way back to 5.2, almost. I mean, we're dealing with a floating point number issue here. That's all that is. Okay. So I'm going to actually go and clean up almost all of this. How much do I want to clean up? Yeah, I think I'm going to clean up everything here. Okay, I'll just clean this, everything except for my softmax. Okay, clean all that up. Let's run that. So there's nothing there. And so if we have this scenario where you've got a neural network that performs classifications between 3 different classes, and a neural network classifies in batches of 3. So after running the softmax activation function with a batch of 3 samples and 3 classes, the network's output layer is going to look like this. Okay, so let's change the way that this looks. So I'm going to do really 3 and 3. Okay, so I'll do a comma and comma again. One more time, one more comma. Do this. This should be actually in here, and this should be here. And then I've got one more set of brackets that I need to add in here to do this really properly. Okay. And of course, now I have to change this to a Numpy array. So np.array. Okay. So this is really what I was saying. So we've got the neural network. It performs 3 classifications. It's in classes of 3 batches, and we're going to run it through softmax activation. And then, so this is really what I'm trying to get at. Just forgive the non-proper formatting or look of the code, but I think this will work. So there's another thing I want to do, right? I want to have my targets. So we'll say class target. And this class target is going to be just like this. It'll be 0, 1, 1. All right. And ultimately what this represents is, a dog or a cat or a cat. Let's just, as an example, dog, cat, comma, cat. So these are our knowns. We know this to be true. We know that the second 2 are cats. I actually should change these values as well. So that'll be 1. This will be 5, and this is 4. This is 0.02. This will be 9. And then finally 0.08. Okay. Now, what we're looking at here is the fact that the first value in the class targets, okay, so this first value in class targets means the first softmax output distribution's intended prediction was the 1 at the 0th index. Okay, so it's really, we're talking about this here. We're matching that up to 0, okay? The model has a 0.7 confidence score that's observed to be a dog. Okay. So that's the confidence score here with the very first one. And the intended target of the second softmax distribution here is matched up with our 1. So that's at index 1. Okay, and that only has really a high confidence score of 0.5. So when you compare this, it says that this is 0.7, this one is 0.5. It actually has a higher confidence that it's a dog than this one having a lower confidence that it's a cat. But when you look at the last one, we've got a 1, but this is the highest number here, our 0.1. Okay, so that confidence level is pretty high in this particular case. So let's have a look at this code here. So if we say for target underscore index. Sorry. Distribution in zip. Okay, we've seen zip before. That's a lowercase zip, sorry. I think we talked about zip in the last video. So we say class target. No. I think the easiest way, copy and paste. Class target, comma, softmax output. Or outputs. Let me change that to an S because it should be pluralized, okay? Class targets should be pluralized. You know, you should try to strive for that level of detail in what you're doing here. Okay, and that's a semicolon here, or colon, it's actually a colon. And then we're gonna print this. We're gonna print our distribution. And in here, we'll have target index. And print. Now, I want you to try to understand what I'm trying to get at here. I'm trying to actually get the highest value within each of the outputs. Okay, I'm trying to get the 7, the 5, and the, or I should say 0.9, 0.5, 0.7. So that's really what my goal is. And you can see that when I run it, that I'm actually getting those proper outputs that I'm looking for. So that's probably the hardest way of doing it, but the better way of doing this, first I'm going to actually just comment these out, and you can see that I've already done that. But again, the better way of doing this with Numpy is actually just to do it this way. So what we're saying is print our softmax outputs, these, and cycle through each of these different arrays here. Okay, and then go to the target class. So when I print this out, you can see that it's different. Now, if I contrast that with this, we'll do them both. And you can see it's coming out in a different format, but that's okay because we're looking for the right things. And I'd like to just clean that up for a minute and not print it out. Okay, I'll leave that alone. And what's this? This is actually returning a list of the confidences at the target indexes of each of the softmax output samples. Okay, so now we're going to apply the negative log to this. And really, you know, this is a lot of line of code, but it's not really that big of a deal. And the way we're going to actually change this is we're going to say negative mp.log and put it into a bracket. We're going to surround that by a bracket and then go to outputs. And I actually don't need to have this here in the middle right now. Okay, so I can take this out. And in here, I'm going to say range. Okay, and then in here, it'll be len, length. And again, inside is going to be soft outputs. Okay, and I should have two brackets there and a comma, and then my class targets. Looks to me like I've got couple of extra too many things there. And I'm missing this right here. That should do it. I could end up having just an imbalance in my brackets, but that's okay. Okay, so I'm getting the numbers that I wanted to get here. So to have an idea of how the model's doing during all of the training, what we're going to do is look for an average loss per batch, right? And we're going to actually use Numpy to do that because we've started down this road, and I think it's just really probably a good way to go. And what I'm going to do is I'm going to remove this print, and I'm going to say neg_log equals, and I suppose I can just get rid of one of the brackets. Okay, so everything I'm doing on the right is now going to be assigned to this negative log value. And below that, what I'm going to say is my average underscore loss, okay, for those batches is going to be np.mean and then negative log. Okay. Just like this. And that's going to be my negative log. Now I'm going to just print, and inside my print is going to be my average loss. Just like that. Let's have a look. Okay, so our average loss now is 0.3851, I suppose. I just want to warn you, this next part's going to get a little bit tricky. And unfortunately, I don't have a really great graphical way to demonstrate it. So do the best you can to follow along with what I'm saying. Okay. So I talked about this idea of one hot encoding, which means, you know, one is on, meaning it's hot, and the rest are actually set to zeros. Okay. And then we've talked before about correct labels possessions, right? So that they're filled with one. Okay, so this kind of thing is what I'm talking about. So when we're talking about the spiral data that we have over here, when we're talking about this, we actually have to add a check to see if there's one hot encoding. And so we're going to have to handle it a little bit different. So we can check this by counting the dimensions. So if targets are single dimensions like a list, okay, if it's a single dimension like a list, or if it's two-dimensional, like, for example, something like a list of lists, right? That's not quite it, but you get the idea. So we've done like individual one-hot encoding, but we can actually do a set of one-hot encoded vectors. Okay, so in this case, we implement a solution using the first equation from this chapter. And that's instead of filtering out confidences at the target labels. So we have really two checks, okay, to perform. Like, is it a single list or is it going to be a list of lists? That's not, well, I guess that's close enough for demonstration purposes. If it's going to be a list of lists. Okay, so we've got two conditions that we need to check. So if, the way we're going to type this is going to be if len, sorry, I don't need this way, but I do need the space. If len is class, see if I get it, targets, good, class targets dot shape. Okay, the shape is equal to 1, colon, then what? So we have to say correct. Do we have correct confidences? No, we don't. Correct underscore confidence. I don't care if I spell it properly or not, to be honest with you. Soft tab outputs. Okay, so we want this, and then now in this particular case, we're really taking almost this, really. Yeah, pretty close to this, if not everything. So I'm gonna copy that, put that here, and let's just confirm that that's really what we wanted. And that to me looks like it is, other than the fact that I've got probably one too many brackets. Yeah, I think I'm good with that. Now the second condition that we have to deal with is elif. Let's grab all of this and do some editing. This is going to equal to 2. Okay, and our Numpy sum. So this is a little bit different here. Okay, so we don't have the same sort of thing here. So I'm going to delete all that. So our correct confidences is going to equal np.sum. And inside the brackets of sum, we're going to say softmax outputs times class targets, comma, axis equals 1. All right. Okay, I'm going to put some notes in here too. All right, so let me give myself some room, and we're going to say so this is the probabilities for the target values. Okay, and here I want to say only if category. I couldn't possibly have spelt that one properly. Categorical labels, and that's okay. And this next one down here, though, is I want to put a comment for only for one hot. Actually, that should be this way. One hot encoded labels. Okay. Now let's keep going because there's a little bit more we need to do here. So let's talk about loss. And our loss, which we've seen before, is really our negative underscore loss, or sorry, log is going to equal negative np dot log. And inside the brackets, it's going to be a correct confidences. Okay, so this. Then one more thing after this, we're going to say average loss. Did we do average loss? Yes, we have. Okay, average loss is going to be equal to np.mean and negative log. And then I'm going to print. And in the print, I'm going to print my average loss. Okay. First and foremost, it doesn't work. And the reason is it says list object has no attribute shape. Okay. But even before that, what I need to do is understand what I'm doing here. Right here, I actually didn't convert that into a NumPy array first, right? Which I need to do. And I'll get rid of the comments here because they're no longer really relevant right now. So I'm going to actually, I'm going to change this right now. So this will be 1 and then 0, 0. Okay, and then I'm going to put a comma, copy this. And that should be changed to 0. This will be 1. And then if you guessed it, this is going to be 1. Sorry, not that. This will be 1 and this will be 0. Okay. And finally, I'm missing a bracket here and another bracket there. And again, this is just really to demonstrate what we had previously to this. Okay, it's just done in an array list. Now I'm going to run this, and let's see if I have another error. And I don't have an error. So I actually did get the average loss calculation, okay, which is what this number is now telling me. So there's one problem that does need to be solved. Okay, so the softmax output, which is also an input to the loss function, consists of numbers in the range of 0 to 1, right? Which makes it a list of confidences. But it says it's possible that the model will have full confidences for one label, making all the remaining confidences 0. But more importantly, we can also get a full confidence value to something that wasn't even a target. Okay, and that's a bit of a problem that we're going to have to deal with. So I really want to just, this is one of those things too, it's a little bit awkward to maybe explain or understand. But I want to talk about this issue here. We've got this log 0, right? You know, up until this point, we're always passing in confidences, or we're passing in values that are really greater than 0. Okay, but what happens if a 0 number gets in there? What can end up happening is when we run this, you can see that we have a runtime warning, divide by 0 encountered in log, you know, the line of code that we wrote. And so one of the things that we're going to have to do is we could try to add a very small value to the confidence to prevent it from being a 0. And so we could do something like this maybe. Let me copy this and I'll put it here, and I'll take out all of this stuff here. Okay, and I don't need the square bracket anymore. I don't think I need that one, but what I can do is instead of 0, I can say 1e minus 7. Okay, and let me run that. Okay, and so you're seeing that I'm getting this very different output, and I'm trying to just add on a minute, minuscule little number on the end of that. Okay, but the problem is that's kind of only one side of it. Like this is 1/10 of a million to the confidence, but it's at its far edge, right? So it's really insignificant, but it can impact the result. Or we could say, all right, let's do 1 plus. We can try and add a full 1 to that. Okay, and so we do that, and now we have an even different outcome here. Okay, but when the model is fully correct in a prediction and puts all the confidences in the proper label, loss ends up becoming a negative value instead of being 0. So what we're going to do is not do 1 on one side and, you know, this on the other. What we're going to do is clip it. And we'll clip it by the same side on either side, or same value on either side. So it means that the lowest possible value will become 1e7. And the highest possible value will be 1 minus 1e7. So slightly less than 1. So it's painfully confusing really what I'm talking about, but what I want to do is make this a negative, okay? So let's print this. And you can see here that it's not so bad of a number. It's pretty close to 1. So it prevents this from being exactly 0, makes it like very small, but it won't make it a negative value and won't bias overall loss, okay, towards the 1. And we're going to use Numpy clip, the Numpy clip method for this, okay? So here we're going to say y underscore pred, or for prediction, clipping, or clipped, is going to equal mp dot clip, and in the brackets we're going to say y underscore pred for prediction, comma 1e minus 7, comma 1 minus 1e minus 7. Okay, and you should be good for bracketing. So again, my suspicions for this particular video is going to be a lot of coding on the side that is going to really result in not too much over here. But what I want to do now is come back into our neural network and really make 2 classes inside of here. I want to just do our common loss class and then our cross entropy loss. Okay, so I think the first one I'm going to do is actually go in and do the common loss class first. And that is just going to be right here. And let me put my comment so I know the difference. Common loss class, that's what I'm going to do. And we'll say class loss. And let's do some notes here. Okay, so we're going to calculate the data in regularization, and didn't spell that right at all, losses, given model output and ground truth values. And so first thing I want to put in here is our def, and it's going to be calculate, and of course it's always self, comma, output, comma, y. Put our semicolon in there, or our colon, sorry. And then sample underscore losses is going to equal self dot forward output, comma, y. Okay. So we've got that part, and then here, what kind of note? I'm good for my notes. Now I'm going to put a note in there, and that's going to be calc sample losses. All right. Next, I'm going to calculate mean loss. And the way I'm going to do that is going to be data underscore loss is going to equal mp.mean and sample losses. Okay, and then the next thing I want to do in here is I want to actually return the loss. Okay. And that's just going to be return data underscore loss. Okay, so that's really it for our common loss, and I'm going to save that. I shouldn't have any errors in it because I really, there shouldn't be an error at this point. So the next thing I do want to do is I'm going to put in, just give myself some space. I want my cross entropy loss. And the way this is going to be is class loss underscore category. I want to make sure I spelled this one proper. Categorical cross entropy, and I'm going to just pass loss in there. All right. Now we're going to do a forward path. And in the forward path, it'll be def. Of course, def always starts with self, comma. Sorry, it should be def forward, self, comma, y underscore pred for prediction, comma, y underscore true. Okay, put in my colon. And from there, we're going to say samples is equal to len and then y pred. Okay. Now, the next thing we're going to do with this is we've got to clip the data to prevent division by 0. And we're going to do that on both sides so that we're not dragging the mean towards the towards any specific value. Okay, let me do the comments here. So I just typed in the note there. I'm going to clip data to prevent division by 0. Then I'm going to clip both sides so that we're not dragging towards a specific value. And so this will be y underscore, y underscore, there it is, pred, underscore clip, and this is going to be np dot clip y underscore pred comma 1e minus 7 comma 1 minus 1e minus 7. Okay, so that should be good there. Now we've got these probabilities for the target values, and remember previously we had our two conditions. Okay, so we went back over to here, and I think what I can do is go over here and grab that, but I'll make some modifications to it after I get it. In fact, no, I think what I'll do is I'll stick it out in you know, we'll do this hydraulically together. Okay, so what I'm going to do is I'll do the comments. So this will be probabilities for target values only if categorical labels. And this is similar to what we just did with the if statement. Okay, and so if our length or len is y underscore true dot shape, and that shape is equal to 1. That's the first condition. Then our correct confidences will equal or be assigned y pred clipped, and we need a square bracket here, and this will be inside the bracket we're going to say range, and it'll be samples, and then outside that we're going to say comma, and then y underscore true. Okay, so that's the first situation that we've got going on here. Now we're going to do an elif and len. I'm just going to take this whole line and set this to 2. And then my next thing is going to be my correct confidences. For the elif is going to be np dot sum. And inside the sum, I want my y pred clipped times y true. And I need a comma, and then finally axis equals 1. So that should be fine for that. Now there's one more thing that we need to do here, and I'll just give it a little bit of space, is we just got to do losses. So this is going to say negative underscore log underscore likelihoods equals negative NP dot log and correct confidences. Okay. And then return what? Negative log likelihoods. So that's just what's going on inside the class. Okay. Now the next thing we have to do is come into here. We're stepping outside of what's going on in the classes, right? And we need to step out of there and go through this and find out where we are next, right? So what we're saying is after we do the softmax activation, okay, then what do we do? And before we can get to the forward, this is where we are going to create our loss function. And the way we're going to do this is, which is pretty simple, and we're just going to say create loss function, and it'll be loss underscore function, and we'll set that to this class that we just created up here. All right. And let me just copy that, come down to here, set that, and I need to put the brackets in there to basically call its constructor. And what else do we need to do? Now we left it off before having these values that we left off here, right? With this print statement on line 26. But so we need to just do one more thing here, because I want to actually calculate finally the loss and then print off the loss. And so let me put in the comments here. So we have two things that are going to happen here. One, we're going to perform a forward pass, okay, through the activation function, and then take the output of the second dense layer and then return that loss. And that is just going to be loss will be loss function here dot calculate and which calculate am I calling here? If you look, and we just are looking at our common loss class, this is what I'm calling right here. Okay, this is what I'm talking about. So when we come back down, we have this calculate function. We've got to have activation 2, okay, as our first argument. And then actually it's no comma, it's dot output, comma, y. And then finally we want to print it off. And print is just going to be print, and it'll be single quotes, loss, colon. Do we want some space? Yeah, we'll put space, a comma, and then loss. And that should do it. So let me save this, and wouldn't be surprised if I have a typo somewhere, but let's run this. Okay, that's okay. I'm going to go up to one layer and I'm going to run this first. Then I'm going to come down here. So I've got a couple things. That's okay. I think one thing for sure I do need to do is sort of address some of my formatting. Seems to be off a little bit. Okay. All right. So, obviously with Python, it has issues with formatting, and you don't want to make that mistake. Something, where your code works and you're chasing your tail because you can't find your error. Now, what does all this mean? Okay. That's what we need to know. So we know two things here, that our average is still, or our values here, because they're random from up here, that's all random. We know that it's still, relatively 0.33. It's a third, okay, of the random model. But the average loss isn't all that great either. Okay, so ultimately what it's saying is that, we haven't trained our model how to correct itself yet, or correct the errors. So one more thing I do want to do next is actually get into the accuracy calculation. So we'll do the accuracy, but ultimately it's important understanding that this isn't a great number, only because this is all random. Okay, so if these numbers aren't great, we're not expecting to get a really great output here as well. I'm going to leave this one and go back to here a little bit. And, I want to do some work in here with accuracy calculation. And I think what I should probably do is just go in and clean all this up. So the way this is cleaned up is very similar to previous example. This is still in a Numpy array, but we're going, I got rid of the other two samples, but we're saying 0, 1, 1. All right, and so let's get into this. We're gonna put in a comment here. And I've got this comment that says calculate values along second axis, or axis of index 1. And we'll do predictions. And this will be Numpy np dot argmax. Okay, argmax. And in here, we're going to say class targets. Class targets here. And this class targets will be along axis 1. All right. And then down here, we'll say as a comment, true evaluates to 1 and false equals 0. Okay. So accuracy equals np dot mean. And inside the mean, we're going to say predictions equals class targets. So we'll say this, predictions equals, and it's a condition, right? We're trying to go for, we're evaluating a condition. It's not assignment, class targets. Okay, and then we're going to just print out this. In here, we'll say single quotes, whatever. Doesn't matter. It's not a spelling contest. This, accuracy. All right, now what happens when we run this? We get an error. One of the reasons we get an error right off the bat is the fact that I'm not accounting for the fact of like the shape. If this targets are one hot encoded, and really I should have clued in when I was doing a condition statement, which did honestly seem a little bit odd to me, that I wasn't actually comparing it. So what I mean by that is if our target are one hot encoded, convert. Okay, and so the way we're going to do this is with the if statement. And this is why I should have really clued into that. So if our length, and we've done this a few times already, class targets dot shape is a shape of 2. Okay, then we should say class targets equals np dot argmax and class targets, comma, axis equals 1. All right. And in fact, that's a little bit wrong too, because really what I need is this in the first within our prediction. All right. Let's run this. Okay, it doesn't like that syntax. That's okay. We can. The issue that I've got with the syntax is the fact that I didn't have my colon there. Let's run this again, and I still have another error. And this error is telling me that I don't have an indentation. All right, run that until I run out of errors. All right, what's interesting here is that I've got an accuracy of 1.0. So just to play around, what I want to do is just change these figures here. Okay, so 7 to 1. And here I want to go from really largest to, we'll just do this. We'll switch these two numbers. I think I'll leave this one alone. All right, and then if I run this, let's see what our accuracy turns into. So now you're seeing that there is a change in the accuracy based on what's going on here. So in a very similar sense to what we did here, when we go back over to our actual neural net that we've been building, if I do it this way here and I add this predictions equals numpy argmax, and we pass in this activation 2 and the output, and we look at the x-axis equal to 1, and then we basically set this y shape equals to 2. Okay, then our y equals numpy.argmax y axis equals 1 again. And then we say that our accuracy equals numpy mean predictions, this here, is equal to, compare that it's equal to y. And if it is, perfect, right? And then we just want to print this out. So what you're seeing here is that we've got this loss here, which we know not to be very good. But look at the accuracy. The accuracy is, not very good either. So I think intuitively that's good to see that we're getting a low accuracy number. Okay, so what I think we're going to do next now is I'm going to run this. We're actually going to learn a little bit more about optimization. That might actually take a bit, come to think of it, but we're going to optimize this. Okay, because we've learned how to do a forward pass through the network and calculate the whether the model is performing poorly or if it's performing well. In our case, it's been pretty poor. Now we're going to look at optimization. All right, so let me run this one more time and see if the numbers change. So the numbers do change, right? At least this did here. Let's run it one more time. And it's relatively staying the same, but it's within that range of 3.4 or 0.34.8. So it's not really doing much anymore. Okay, it went up to 4.2. Because we have random numbers up there, random values being generated, that's why we're going to get that effect. Okay, so what I want to do now is actually move on to optimization. Okay, I admit I just had a massive technical failure. I recorded a whole bunch of video, about 10 minutes worth, and had my mute button on the whole time. Didn't see the little red flashing light right in front of my face. That's okay, because I think it's less painful if I walk you through this as opposed to you guys watching me type, because I think that in itself is really, really a big challenge. So nothing up here has changed in what we're doing. Okay, and nothing in the spiral data is changing. So, I'll continue. I'm just going to run through it just to make sure everything is still outputting the way we want, which it is. And what I've gone ahead and done is I've created these helper variables. Okay, and within that, we're initializing our lowest loss level to this. It's 7 digits. It's 999 followed by 4 nines. Okay, so that's going to be the initial values. And so what we've done there next is we've created this best dense one weights. Okay, and then we're taking the dense one weights and we're just copying it. So this becomes a copy and we're then assigning it to here. And we're also doing the exact same thing with the bias. So we're copying the bias values and assigning it to this best dense one. And then right after that, immediately, we're doing the same thing with our dense 2. Okay, we're taking the weights, copying them, and assigning them to best dense 2 weights, and then best dense 2 bias. That's all we've done really so far at this point. However, what I now actually need to do is take all of this information because I want to show you one thing. I don't want to go too far down. We've created this iteration. And within this iteration, we've got a range of 10,000. And we're going to generate a new set of weights for each iteration. Okay, and we're going to iterate this. We're going to initialize the loss to this really large value. And then we're going to just decrease it with a new lower loss that we find. And so we're copying the bias and the weights. And this isn't, just to make sure that we're getting an actual copy instead of a reference to it. And so we initiate as many, iterate as many times as we want. And then we're going to pick random values for weights and biases and save the weights and biases if they generate the lowest loss that we observe. Okay, so that's really what we're doing. But I need to basically take some of this stuff here. And I want to show you that I've created this 4 iteration in range 10,000. And then I've generated these new sets of weights. So it's start on the right, okay, 0.05 times Numpy, random, 23, okay, and then that's going to be assigned to dense 1 weights. Okay, and then the same thing, we're going to do exactly the same thing with our bias. And then again for dense 2, we'll do the same for weights and bias, of course. And then make sure we're matching up. Okay, and these two will remain the same. All right, so I've done that piece there, but what I want to do is I want to keep this indentation, right? Because we're going to iterate through this entire thing. So now what I can do is take all of this code, take that out of there, and I want to now put it here. But I want to make sure that the indentation is correct. All right, and I think for now, I'll get rid of this print. I don't need the print. Okay. And I do need to push this over too and keep the formatting as well. This print, I think I'm just going to comment that out for now. And when I look at this line here, this prediction of argmax activation to output axis 1, that's fine. And my accuracy is fine as well. But I need to make some modifications. So I can actually go in now and take this out. Okay, and again, I'm going to push this over because this all needs to be inside of the 4 or what we're iterating through. In fact, I'm going to take this out altogether. Raise that up a little bit because I want to put some commenting in there. So I've added my comment here. What I'm doing is I'm calculating accuracy from the output of activation 2 and the targets. Okay, and then I'm going to calculate the values along the first axis right here. Right. And then I'm just actually going to do the accuracy like we had previously already done. And I'm going to check this to make sure nothing's wrong. Okay, we have many values in there, especially in terms of our accuracy. It's quite a few values, so much that I have to scroll. So definitely, I'm happy that nothing's wrong, but I'm going to take out the print statement for now. Okay, so this next step is important. And what it is if the loss is smaller, then print and save the weights and the biases. Okay, so we're going to just save those to a side. So what we're going to do is this. If loss is less than lowest loss, put my colon, and then what? We're going to say print, let's say new set of weights found, comma, iteration. Okay, and finish that with the quote. Sorry, I've got to fix these quotes because they're not proper for what I want to do. There. And so that's the first part. Now, comma, iteration, comma, single quotes, loss, colon, comma, loss. That's the actual values we'll get, comma. We'll do single quotes, accuracy, and put in our colon, comma, accuracy. Okay, so this is going to probably print out quite a lot of stuff. So I went ahead and ran this, and as expected, there's almost 10,000 iterations that we've gone through. Okay, so it's quite a lot. And you can see here that the accuracy doesn't really change all that much. The variation is pretty low. There's a 0.29, okay? So it's not a huge deviation whatsoever. So what I'm going to do is just kind of comment that out for now, run it, and then I'll uncomment it because we're not actually done with this this part at all. Okay, so what I want to do next is, because we're talked about saving the weights and the biases, right? So if I say best, what are my options? Best dense 1 weights is going to equal to dense 1 dot weights dot copy. And I'll do the same thing really with, in fact, just wondering if I can just go and grab it here. Yeah, I think I'll get everything here. Probably be the best way of doing this, least painful for you guys. And I'll just have to add the word. No, it should be good, actually. Let's see. Yeah, just need to change the formatting. Okay, or my indentation, sorry. Okay, and this is all fine, but like I said, we want the lowest loss. Okay, so we want lowest loss to be assigned the value from loss. Okay, so I've gone ahead and I've run this, okay, with this new updated code. And you can see what's happening here, right? Is we have a much smaller density of values, where I think last time we had 9,999. Here we seem to have about 9. We have iterated through and identified 9 iterations. So when we look about this, the biggest or most dramatic thing that we're seeing is that there's, you know, a lot less iterations. But, you know, we look at our loss, our loss really isn't all that different or significant, really. And our accuracy is, you know, it's not very improved at all. Okay. So we still have some more work to do, I think, here. So what happens if I run it again? We'll see. Okay, so that was a significant difference. What are we getting in terms of our accuracy? Not great, right? Let's run it again. Okay, so things are changing. Everything seems to be relatively range bound. You know, this 0.33, a 0.4, a 0.36, 37, and even a 0.35. So accuracy is not that great. Our loss is really within the same zone, right? What if I go here and I change this to a 9? So instead of 10,000, it's actually 90,000. Let's see what happens there. Again, not really all that impressive. Let's run it again. Interesting. Okay. Not really much going on here again. So it shows that the size isn't really the factor that we're getting at here, right? So if I change that back to 10, I'll run that. You know, same sort of result. So we know that loss continues to drop if we have a much bigger sample size, but accuracy isn't changing really. So it doesn't seem like it's a reliable method for minimizing the loss. I could change this to even 1 billion, but I suspect that we'd get the same sort of result. So even with this data set, we see that randomly searching for weights and bias combinations could take forever. So another idea is, instead of setting the parameters with randomly chosen values for each iteration, we could apply a fraction of these values to the parameters. Okay, so weights will be updated from what we're currently getting with the lowest loss, instead of sort of randomly aiming for that value. So if we make an adjustment to decrease the loss, then we can make it the new point to adjust from. So if loss instead increases due to the adjustment, then we'll revert to the previous point. Okay, so using this code from up here, where is it? Here, we can make this simple adjustment. Okay, so all I'm actually going to do right here is just add a plus sign. So this is all going to be plus equals. That's all I want to do at this point. I'm just going to, randomly sort of adjust this. So if the adjustment decreases the loss, we'll make this the new point to adjust from. Okay. If the loss increases due to the adjustment, then we're going to revert to the previous point. And the way we need to do that is to go down here and supplement or modify this particular block of code, right? And we're going to do that with an else, or really an else. Okay, so else, what we're going to do is now take this, all this code right here. Sorry, not this one. Is this what I want? I think what I'll do is I'll just really type out the first two. So dense one dot weight will be now equal to best dense biased weights, or sorry, best dense one weights dot copy. Okay. And then here, after this copy, it'll be dense one dot bias is going to be equal to best dense one bias dot copy. Okay, so that's again a little bit of a tongue twister to say that. So I'll copy that and then just convert that all to dense 2. Let's add a comment too. So this will be revert weights and biases. All right. Okay, so time to give this a bit of a run through, okay? So let's see, do we have any big issues? Okay, so that's a pretty good sample size, I think. And what are we getting here now? We are actually seeing, you know, not the best, but we're seeing some sort of change in our accuracy. And you notice, we have a almost 10,000 sample size, and we're getting down to these ones here. So it's not a lot. Let's see if I can run it again. Okay, so this one looks like a pretty large sample, but you can see that our accuracy is changing. Okay, I'm seeing some 0.41, 42. It still seems a little bit range bound to me. 0.43. I think 0.43 is the highest I've seen. I could be wrong. Let's try one more. Yeah, we're still sort of in that area. So really, what can we say about this? Ultimately, in this particular training set, there's not really a lot of progress. I'll be perfectly honest with you here. And it is a difficult problem, and it has a lot to do with the training set that we are actually using, right? Remember, this is randomized data up here, very randomized. Now, had I changed this data set into something different, maybe, more than likely we would have got a different result altogether. And also keep in mind that this is a spiral data set. Now, there are many, many reasons why in this particular case, we're not getting our loss to change very much, and we're not getting this accuracy. We haven't even begun to talk about derivatives. We haven't talked about backpropagation. There's a lot more to this. Okay, so if your sample size was different, or even not so much the size, but the composition of the sample, maybe if this wasn't actually in this shape, right, a spiral, if this was, for example, a different configuration where maybe each of these clusters would be vertical, you would more than likely get a much higher accuracy rate. But because these points are really all over the place, and they've been randomized this way, this is really why we're seeing that right now, that our accuracy really doesn't know how to handle this. Okay, and so if you were to try to go through and optimize this really, really well to get high accuracy, we'd still have to talk about derivatives. We'd still have to go through all the backpropagation. And then we'd have to come back, revisit the whole optimization. But we're not going to do that today, that's for sure. But what I'm going to do is actually end the video. And if you're to this point and you're understanding what's going on, I think that in itself is a great little victory. So take that and make sure that you understand really what's going on in all of this particular code. Before I go, what I want to do is leave you with this particular resource that I have found. I think I found it through Sendex as well. It is cs231n.github.io/neural networks case study. It looks to me like it's a course for something. I'm not entirely sure, but it looks pretty good. But anyway, it's spring 2020. And so if you go back, you can look at this convolutional neural network for visual recognition. This is this little case study, or maybe that's just the title of the course. But in this particular thing, there's a whole section about softmax linear classifiers, compute the loss. And you'll see all, more of the math explained if that is something that you really feel that you need. But you can, mix that in with the Python programming and the code. And you'll see that a lot of the numbers here are similar to what we've done. And as you go down, you'll see some differences in here in the code, which is perfectly good. And you'll see at this point, they get a 49%. Okay, when they're evaluating the training set accuracy for this particular data set. And as they go through and they're doing some further training, and they go through, they actually get down to the bottom and you'll see that they're actually able to print out a 98%. Okay. So if you want more, that's fine. Just remember, go check out this case study and work through that as well. I think it's a really good resource to have. Okay. Anyway, I'm going to end the video there and wish you guys all luck, and hopefully we'll see you next week. Okay. Thanks.